Hi, so here's a simulation that I put a short out of a while back, and it's a double pendulum, and it's all based on the physics and the equations of motion that you can derive, and I'll show you that a little bit later. You have control over initial conditions and initial positions and weights of the masses. Here it's a pendulum with lengths and masses, and those are all things that you can adjust to make any kind of double pendulum you want. And I'm also using the Runge Kutta fourth order integration scheme that I have in another video, and I'll go through that a little bit here, but I think I went through it kind of in enough detail on the other one, but I'll go through a little bit here because maybe some people need it a second time. That's kind of typical. So I'm using the fourth order Runge Kutta method to do the time integration, where you start off with some initial conditions and just let it go and do whatever you want. So let me go into the node network here. So first, here's the problem. Double pendulum, two masses, M1, M2, two lengths, L1, L2, and the angles that they sweep out are theta 1 and theta 2. So if you have your L's and thetas, you can write out the positions of each one at each increment of time. And then here I'm showing you real quickly how you can derive the equations of motion, starting with Lagrangian and going through that. And you can look this up online and get the full gory details of the derivation. So this is something you'll see in like a basic physics class. The kinetic energy and potential energy go into what's called Lagrangian, and then you can use Lagrangian to write out the equations of motion. Here they are. Where m is the sum of the two masses, the delta theta is the difference between the two thetas. And then here I'm going to show you the Runge Kutta method. Here's the equations kind of written out for you. The time integration is just the x of n plus 1 is equal to x of n plus sum of these k values. And your delta t is your time increment. And your k values are determined by the equations that you've set up in your system. And your system, of course, here is the x dot equals f, and that's a function of x and possibly t. If you have like a forcing function, that's a function of t. So it's actually x and t. And so the Runge Kutta, it uses this equation, your f of x, whatever that is, to determine what your k1, k2, k3, and k4. And you can see that not only are your k's dependent on each other, but the time increment is shifting by half of your increment and then by the full increment. So let me clean that up and let's get started. So here I have, going into a simulation zone, all the starting values, my thetas, my theta dots, that's the time derivative of theta, your rotational velocities, time, and that's the starting point. It starts at time 0, your dt, time increment, the two masses, the two lengths, and then the gravity constant there. And so here, those go into this node that I'm calling K1, and I have this repeated 4 times because it's the same function, f of x and t. It's just the inputs are a little bit different. So here I'm taking t times f of d theta 1 dt, and then the same multiplication with respect to theta dot 2, and then theta 1 and theta 2. dividing by 2, and then I'm adding that to the x of n that goes into it. And here you have to think of it as you're writing two equations, so you have a theta 1 equation and a theta 2 equation. And those were the two equations that I showed earlier. You can go back in the video and pause if you need to take a look at that again. So that takes care of the velocity terms, but then there's also displacement terms that need to be incremented, because really there's a theta 1, theta 2, theta 1 dot, theta 2 dot are the four variables that are changing throughout the simulation. So those all go into K2, and inside the K1, K2, K3, and K4 is the same structure. And so here I'm doing the same thing. I'm using K1 as the starting point, and then the delta t is divided by 2, and that's multiplied by the K1 that is added to x of n, and that goes into to the input of K3, and then K3 there's a similar thing. I'm taking the x of n and adding it to K2 times delta t over 2. I'm kind of showing you here how that works. And that all goes into K4. So then K3, there's a similar thing. You're taking x of n and adding K2 dt over 2 into it, and then that goes into K4, where it's multiplied by delta t and then added to x of n. And then those all get added together. And here I have 4 node groups here, because it's the same 4 values that are being combined, but for different state variables. There's theta 1, theta 2, theta 1 dot, theta 2 dot. And so this is just the summation there, the delta t over 6 multiplied by K1 plus 2K2 plus 2K3 plus K4, and then that's added to, outside of this, that's added to the original x of n. And that gets you your x of n plus 1, sorry. So this is the same calculation, but when you're following through the x1 and when you're following through x2 and then x1 dot and x2 dot. So then you can see I'm adding theta 1, theta 2, theta 1 dot, theta 2 dot to those summed values. And then here I'm storing the values as attributes, so then I can go over here and open up the spreadsheet, and then you can see them. I have 2 instances. I have a couple of points going in. If I take a look at the geometry here, you can see that's the point. And I'm, sorry, it's a single point, but I'm doing all these calculations on that point. And then when I get out of the simulation output, I'm actually doing something where I'm creating instances on points and using these theta 1, theta 2 values to perform some adjustments of the geometry. So I'm doing all the calculations and then using those calculations to make the animation move, where I have cylinders and balls and things representing the double pendulum. So here I take those outputs from the simulation and I'm creating XY coordinates for each of those endpoints where the masses are. Of course, the origin is going to be the pivot point. That makes it easy. So I have 2 points going in, and I'm doing an instance on point, and I'm using the index and putting it through a compare node to select whether I'm performing functions on the first point or the second point. And I'm creating a couple instances which are icospheres, and then setting the position based on the x1, y1, x2, y2 that I'm calculating from the equations that I'm showing on the top here. And then I'm doing shade smooth there. And you can see I'm just following the equations that I have written up on top. And then I'm adding a couple of cylinders. Of course, here I'm giving them materials, and the cylinders, the position of the origin and the endpoint are all determined by this x1, y1, x2, y2 that are being calculated. So the start and end points are just those vectors going in. So I have x, y, z going in there. And then I'm doing a curve to mesh so I can apply some materials to them. And that's about it. That's the whole Runge Kutta method. So now if I go into this K1, and it's the same if I go into K2, K3, or K4, it's the same thing. And here's where I set up the equations of motion. So here are the equations of motion again, just so you can kind of follow along. If I go to the inputs, I have dt, the derivative of theta 1, derivative of theta 2, m1, theta 1, theta 2, g, m2, l1, and l2 going in. And I'm trying to make use of these extra little nodes that you can do with the node wrangler. I think it's shift and then right mouse swipe over a node, and then you can actually go into where it says node over here. If you select that particular node and give it a label, that's why I got all these M2s and L2s to kind of keep track of it all. And I kind of broke it out into sections where I'm doing the calculations, and I'm sort of writing it up here where I'm going to have a frame around A, B, and then those are going to go together to make C. And then just to try and make it clear to myself, then the cosine d theta is going into A, and you can see that d theta 1 dt is going to the power of 2, and then m2, l1 are being multiplied. Those two are being multiplied, and that goes to make A. So then you can see that m2 is multiplied by l2, which is multiplied by the second power of theta 2 dot. And so we can take those two and then add them and multiply by sine of delta theta, and that makes C. And then if we go to the next portion of the first equation, there's D and E and M. Remember, that's M1 plus M2, so that's an addition, and then that's being multiplied by G, and then that's multiplied by sine theta 1, and that makes D. And then I'm writing, kind of breaking it up into pieces on the second equation where I have an F, a G, an H, and an I. So E is the next part, and you can see that G is being multiplied by M2, and then that's being multiplied by sine theta 2, and then there's another multiplication of that times the sine theta 2, sine theta 2 times cosine d theta, and that makes E. Then here I have M, capital M being M1 plus M2, and then L1 is being multiplied by that to get ML1. And then the difference in the thetas is going into sine function, so that's sine d theta, and that's being multiplied by F. G is being calculated in its own separate block, and so that's M2 times L2 times theta 2 dot to the second power times cosine delta theta. And then down below, we're going through the calculations again for the rest of it. Here, And here I'm creating this denominator that is L2 alpha, and alpha here is, here's the equation for it, it's m1 plus m2 times sine squared delta theta. So once I get the denominators for equation 1 and equation 2, those can be used to as a divider in a divide node. Once I get the whole equation within those brackets, then I can just divide by L2 alpha and get that part of it. And here I'm showing quickly the equations for H. It's pretty clear what these should be. There's multiplication nodes everywhere. And I'm trying to write out what, make some nodes there so you know what's going in, because it's a little hard to kind of sort this all out when the equations are a little involved like this. So there's a subtraction here between H and I, and then that's added to the rest of it. So that's basically it. Once you get all the equations set up, you just feed those into the outputs of that simulation node. And then once you do that, it's pretty much ready to go. All you need to do is click the play button, select the initial conditions to whatever you want, and let it go. So if you like this video, click like or subscribe or both. Have a good one. Bye.